So now we have seen the applications of vector processing. So these are the some of the applications of vector processing. Now we try to see what is meant by a vector. So vector is basically a vector v of length n is represented by a vector v of length n is represented by a row vector. So this is a vector and these are called elements in the vector. It is having n vectors. If you take an example 1, 2, 3, 4, 5. So I can call this as one vector and this vector has 5 elements 1, 2, 3, 4, 5. And if I want to access the third element, I should say v of 3. V of 3 is equals to 3. V of 4 is equals to 4. And second important thing is that this vector has one row and 1, 2, 3, 4, 5 columns. So one row, 5 columns vector. So this is called if you take an example, A is a vector 10, 5, 15, 20. It contains 4 elements. Then it has one row, 4 columns. So column 1, column 2, column 3, column 4, and it has only one row, 4 columns. So this is called 1 by 4 vector. This is called a row vector. A row vector is a vector which has one row and n columns. N is nothing but number of elements in the vector. Now you see there is also exist a column vector. So the column vector is, you can imagine, it has n rows, 1, 2, 3, dash, 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 n rows by one column. So it has n row by one column. This is called column vector. So we have row vector, column vector. In column vector, what happens? There is only one column. And in case of row vector, I have n number of rows. So when I have column vector v, v1, v2 up to vn, then this is called n rows and into one column. So we understand the column vector and row vector. If you have a column vector v1, v2 up to vn is a column vector which have n rows and one column, and it contains n rows and one column. These n rows and one column has an important column vector. Now we try to see how to access the elements in a row vector or column vector. The element vi of vector v is written as v of I. V of I. If we want to access third element you should say v of 3. This v of I and the index I refers to a memory address or register where the number is stored. So in case of v of I, the index I refers to a memory address. So here I refers to a memory address. In case of v of I refers to memory address, or it refers to a vector v of length n is represented by a row vector. The element vi of vector v is written as v of I, and the index I refers to a memory address or a register. Now let us consider a simple program in assembly language which takes two vectors as the input a and b of length 100 and put the result in vector c. So the input is one vector which contains a1, a2 up to a100, and b is another vector which contains b1, b2 up to b100, and you will add a vectors a1 comma b1, a2 comma b2, comma dash 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 a100 plus b100. Add two vectors a plus b and store in a third vector c. I hope you are understanding the problem. Here the problem is you are supposed to add two vectors. There is vector a and vector b, and these two vectors can be are like one is a1 to a100, b1 to b100, and you have to add corresponding elements a1 plus b1, a2 plus b2, and a100, like that. It should continue to a100 to b100 and store in a third vector c. So here c is a third vector. This is the goal. How this can be achieved? By using uh, a conventional computer. How it is achieved in a how to in simple way, how two vectors can be added in a conventional computer which has sequential computing capability is written here. It is using a assembly language program. So this assembly language program, what it does, first it will initiate I to 0. I is an index variable. Next, read a of 0. Read a of I means read a of 0. Read b of I means read b of 0. Next, add a of 0 plus b of 0 and store in c of 0. So this statement, what it says, store c of I is equals to add a of I plus b of I and store the value in c of I. Now increment I to next element. Now I points to 1. Test if I value is less than 100. If I value is less than 100, go to 20. In 20, what? Again you should read a of 1 and b of 1. Similarly, perform addition and increment I value to 2. And see whether 2 is less than or equals to 100. Then again go to and repeat this process until I value becomes 100. Once it reaches 100, now I is incremented to 101 If 101 less than or equals to 100, it's false, so it will continue. So here it is using a loop. To be say simple words, this statement says that normal or conventional computer uses loop to execute or iterate over elements in a vector. You may have a parallel programming language, but if your conventional computer have a sequential capability, then it is not possible. It will implement, you have to write a loop. Now we see if you have a vector processor, what happens. So a computer capable of vector processing eliminates the overhead associated with the time it takes to fetch and execute the instructions in a program loop. So what happens? If you have a vector processor, then you don't use loops. Simple word. If you have a vector processor, then you no need to use loop. Simple. If you have a vector processor, then loop is not required to access all the elements in a vector. Then how it is implemented means it allows operations to be specified with a single vector instruction of the form. Single vector of the instruction of the form. First you take a vector. This is called indexing, starting index and ending index. This is starting index, this is ending index, a of 1 to 100 plus b of 1 to 100. What happens is a of 1 is added to b of 1, a of 2 is added to b of 2, like that it goes up to a of 100 added to b of 100 and store in c of c 1 to 100. So add a of 1 and b of 1 and store in c of 1. Add a of 2 with b of 2, store in c of 2. Like that it continues, add a of 100 with b of 100 and store in c of 100. So what happens here with single, it is replacing the entire code. If you have a vector processor, this whole thing can be replaced by a single instruction. A of 100 is equals to C of 100 is equals to A of 1 to 100 plus B of 1 to 100. So if you have, this is the power of vector processing. It doesn't take, it takes all the elements. The vector processor works on entire array, entire vector. You need not to fetch each element, individual element in a vector. So I hope you are understanding how the vector processor speeds up the computing capability, means by this way. Now let us see the instruction format of the vector processor. This is instruction format. The first statement says operation code. Operation code, what it specifies, whether you need to perform addition, subtraction, multiplication or division. So you have to see what type of operation is required to perform, whether it's a addition, subtraction, multiplication and division. This is called operation code. Next we have base address of the source one, that is address of vector A, base address of source 2, address of vector B, base address of the destination, vector C, and vector length. So the best example is this one. Add A, comma B, comma C, comma 100. What happens? So take the elements A of 1 to 100, take the elements B 1 to 100, add corresponding elements and store in C of 1 to 100. So the instruction format is like, first is operation code, what operation you require to perform, and the base address of source 1, base address of source 2, and base address of the destination, and the vector length. This is the instruction format of a vector processor. Now we see a simple operation which is called matrix multiplication. So what this matrix multiplication do is that, let us consider the multiplication of two 3 by 3 matrices. So this is one matrix 3 by 3, this is another matrix 3 by 3, and of course results also you will get 3 by 3. I need not to explain mathematics. Number of columns in the first matrix should match with the number of rows. So if you take a matrix like 3 by 2 matrix and 2 by 3 matrix, means the columns in the first matrix should match with the rows in the second matrix. So the resultant would be 3 by 3. You know about matrix multiplication, right? Similarly, here A is one vector, B is one vector, you are doing matrix multiplication, you are getting 3. This is 3 by 3 size, this is 3 by 3, this is 3 by 3. See, these concepts are really important to understand if you want to work in a machine learning or data science or artificial intelligence. So the product matrix C is a 3 by 3 matrix whose elements are related to elements of A and B by inner product. You know about matrix multiplication, right? Take the row, first column, R1 and C1, A11, B11. So A12, B21, A13, B31. So A IK multiplied by B Kj. K is equals to 1 to 3 is nothing but Cij. So this is the formula for matrix multiplication. I hope you are trying to get how, means it's really important to understand. Here A11 is multiplied to B11 plus A12 is multiplied by B21 plus C13 is multiplied by B3 1. So which is common here? A12 B21, C13 C31, A11 B11. So this is, if you take this is here I is equals to 1 2 3, and if it is like j is equals to 1 2 3, then you can say aik is multiplied by bkj, and k is equals to 1 to 2. You can write it like aik is multiplied by pkj, and you are storing in cij, where k is equals to 1 to 3. 1 to 3 ik kj. So this is the formula for implementing matrix multiplication. The product matrix is a 3 by 3 matrix whose elements are related to the elements of A and B by the inner product. So this is called inner product. For example, the number in the first row and first column of matrix C is calculated by saying I is equals to 1, J is equals to 1 to obtain. Just now we have seen A11 multiplied by B11 plus A12 multiplied by B21 plus A13 multiplied by B2. And you have to add these three product terms. For that reason, we are saying sigma k is equals to 1 to 3. This requires 3 multiplications, and after initializing C11 to 0, 3 additions. Not 3 additions, 2 additions. So this is called one multiplication, second multiplication, third multiplication, and required 2 additions, not 3. One assignment. So the total number of additions or multiplication required is equals to, since there are 9 elements, for one element you require 3 multiplication. For one element you require. Obviously for 9 elements you will have 9 into 3. That is 27 multiplications are required. In general, the inner product consists of sum of k product terms of the form. If you take a general case, C is equals to A1 B1 plus A2 B2, A3 B3, A4 B4, and up to AK BK. In a typical application, the value of k may be 100 or even 1000. That means the length of A is a matrix whose value can be 1000 by 1000 rows and columns. B can be 1000 by 1000, or even 10,000, or even 1 lakh, can even go beyond 1000. So in a typical application, the value of k may be 100 or even 1000. The inner product calculation in a pipeline vector processor is shown below. Now we have to calculate the inner product, and we have to calculate the inner product. This inner product calculation is very important. So let's try to understand this inner product. So the inner product calculation on a pipeline vector processor is shown below, and the floating point adder and multiplier are assumed to have 4 segments of each. We are using floating point adder because the matrix may contain integer or real value, so we are using floating point adder, and multiplier are assumed to have 4 segments each, and we are using pipeline technique along with vector processor. So we are using pipeline with vector processor. See, here I have source A, here I have source B. This source A and source B is given to a pipeline which has 4 stages: S1, S2, S3, S4. Multiplier pipeline, and what this multiplier pipeline will do: multiply A11 B11 plus A12 B21 plus A13 B31. So multiply all this, will do in the multiplier, and give it to adder. So this adder will multiply all the items. So this is the figure explaining pipeline for calculating inner product. So why we are calling as a pipeline means, here one stage, this is another stage. This again contains substages 1, 2, 3, 4, 5, 6, 7, 8. Next, the result is again taken here, and when you multiply some items, you will add and make here add for the next item A11 B11. If you give to this A11, here you multiply. How it works means, here you multiply A11 and B11, give it to here, it will add pipeline, nothing is there, so here you will have A11 and B11. Next time when you have A12 B21, it is multiplied with A11 plus B11. So this line contains A12 and B21, A11 and B11, A12 and B21. Similarly, the next item will come. A13 B31 is added to the result of these two. So it goes on like this. So this is a simple example of how a pipelining can be implemented for doing vector operations. So the 4 partial sums are added to final sum. So A11 and B11, A11 and B11 added to, here if you take A11, A2 B2, A1 B1, A3 B3, A4 B4. These 4 partial sums are added to form the final sum. A55, A66, A7, B7, A8, B8. So it goes on continue like this. So what happens here, if you have a pipeline along with vector processor, then can you say that pipelining alone works here? No, definitely you need a vector processor. See, here if you have, if the source is A is a vector, remember, which contains 1 to 100 elements. B is again a vector which contains 100 elements. And these calculation has to be performed parallelly on each element while doing matrix multiplication. It's not like you perform A11, B11, then again wait for A12, B12 to fetch. No. All these A11, B11, A12, B12, all these elements in vector A and B should be readily available. You cannot go and fetch each element from the array. So if these two vectors has to be ready, then it should be a vector processor. Then it has to be a vector processor. So the vector processor makes all array elements ready, and this pipeline technique allows overlapping this multiplication and addition. See, for overlapping this multiplication and addition operation, you are implementing pipeline, but for getting the values, where all the values of A and all the values of B, you are maintaining a vector processor. And it's very important to maintain the vector processor, otherwise it is not possible, right? So I hope you are getting, we are implementing matrix multiplication with pipeline vector processing. Here you are using pipeline along with the vector processing. So this is called pipeline vector processing.